Welcome to the lecture 7, Unconstrained Optimization, Single Variable Problem. So we are still focusing on single variable, but today we will discuss a new method known as Newton-Raphson method. In the last lecture, we basically discussed the idea behind golden section search algorithm, and it was essentially an interval bounding algorithm, but we will see how a completely different types of algorithm which falls into derivative based method can be also used to solve a single variable problem. So let's go on and let's learn some of the unique features of the Newton-Raphson method. Okay. First thing that I want to mention is that the Newton-Raphson method is a derivative-based method, and this is considerably or significantly different than the approach that was taken in the golden section method. In the golden section approach, what we did is we had initially a bound, our interval, right? We essentially began with some interval. We started with A and B values. That was the interval. And then we found sampled 2 points, x1 and x2. And then we reduced in the iterative fashion, we will reducing this initial interval into smaller interval I dash, right? So I double dash, the interval was still reducing. In I iteration 3, the interval was further reducing, right? And that was the approach. But in this approach, which is basically interval reduction approach, where we are making the intervals smaller and smaller and smaller to locate the optimal point, right, or optimal problem, and that is different in the Newton-Raphson method, where we are now focusing on a derivative-based approach, or an approach where we are going to use the derivative information of the function for which we are trying to find the optimization to solve for this problem. So that's the key distinction. So here we will focus on the derivative-based approach, right? And why this is useful? So if the function or the problem that we have, right, is smooth and continuously differentiable, then we can get very, very highly efficient algorithm that could be way faster than the golden section algorithm. In the golden section algorithm, we are doing iteration, we are reducing the interval, but further efficiencies could be gained if we are using a derivative-based approach, such as Newton-Raphson approach. The second thing that I want to mention that, especially if the functions are higher order functions or completely nonlinear functions, then we might have a significant speed up in how fast we can approach and find the optimal solution. So that's another advantage of the derivative based method. However, at this point of time, I should also say what is the disadvantage of this sort of approach. Let's say if you have a function for which the derivative is not known, or a function which is not continuous, then in that case we will not be able to use a Newton-based approach to solve for optimization problem, and that is one of the limitations of the Newton-Raphson method. Before I go on and talk about the next set of intuitions and the intuitive aspect behind the Newton-Raphson method, one of the things that I want to mention is this is a very important class of algorithm, especially from the machine learning point of view. The ideas or the basic intuitive concepts that we are going to discuss in the Newton-Raphson methods essentially are also underlying some of the latest and greatest algorithms that are the optimization algorithms that are used in machine learning domain, such as stochastic gradient descent. And later on, we will also, talk about the gradient descent approach, and you will see that the gradient descent approach is motivated by the Newton-Raphson method. So in that sense, there are some connections, and it's a useful method to focus on. However, again, I want to repeat, right now we are still focusing on a single variable problem, and then, hopefully from the next, lecture onward, we will start focusing on multiple variable problems per se. Okay, so with that, let's get into some intuitive understanding of what Newton-Raphson method is and how it can be used for solving optimization problems.